Good afternoon, and welcome to the Solar Heliophysics lecture given by David Mccomas. And we have a distinguished visitor to introduce David, and you always know, and I should have said this before when we introduced Fran, the magnitude of the person being honored by the magnitude of the person doing the introducing. That's why I'm not doing the introducing, and we have today here Professor Margaret Carlson, who's going to introduce David. Thank you.
Well, I'm going to start by saying welcome to everybody to the second of my two favorite parts of an AGU meeting, the Van Allen Lecture and the Parker Lecture. I think that just by the turnout, you can see that I'm not alone in feeling this is a high priority part of any AGU meeting. So I want to say a few words about the Parker Lecture before I introduce our Lecturer of the Year. It was established in 1989 to honor Eugene N. Parker, the father of solar wind theory, and of the eponymous Parker spiral orientation of the interplanetary magnetic field, and now the Parker Solar Probe. Parker himself presented the first lecture in the series, and the succeeding lecturers have been a who's who of scientists who have made significant contributions to the fields of solar and heliospheric physics. Today's lecturer adds luminosity to a distinguished list. So in introducing Dave Mccomas, where should I start? I think the best is to start in 1983, when a young man in a hurry, an Eagle Scout with 3 years' experience as a member of the technical staff at Los Alamos, showed up at UCLA ready to impress any and all. Indeed, he impressed any and all, and he hurried. He completed his PhD work on magnetotail current sheets at Earth, Venus, and comets in record time. And from then on, I've been keeping an eye on you, Dave. When Dave received the McElwain Award, this is not his first AGU award, in 1993, he remarked that his PhD advisor, Chris Russell, had shown him the value of intuition in understanding physical phenomena. That intuition must have been working overtime as he moved from one to another major contribution in heliospheric physics. It's hard to know where to begin in discussing these contributions because they take so many forms, and that's really rare among our superstars. He led NASA missions TWINS, IBEX, and now IMAP. He led instrument teams for multiple additional solar, wind, and planetary missions. He developed or participated in the development of new and sorely needed instrumentation for the measurement of low-energy plasmas, including plasma instruments on ACE, Ulysses, and Cassini. And much appreciated by his colleagues, he shared his data generously. Sometimes those who excel at development of hardware and or at the organization and leadership demanded to be a PI leave the task of scientific interpretation and publication to other members of the team. But that's not true of Dave. On a recent bibliography, he lists 662 refereed papers with another long list of those in press or under review. His work matters. It has been cited more than 29,000 times, according to Google Scholar. It would be easy to continue to list Dave's achievements, but instead I want to single out my two favorite scientific contributions, pieces of much bigger and much more extensive work. Both are brilliant examples of creative visual representation of quantitative data. Using Ulysses data, Dave provided a single figure that almost anyone studying the solar wind will recall instantly. On a polar plot, he used radial distance to represent the radial speed of the solar wind as a function of latitude, and he used color to represent the orientation of the magnetic field, summarizing a full orbit of data in a single figure. One need not read the paper to understand that the fast solar wind is localized near the poles and that the dominant field reverses sense across the equator. My second favorite is the amazing representation of half a year of IBEX data that shows the distribution on the plane of the sky of ENAs, that's energetic neutral atoms, whose source is at the heliopause. It forms a localized ribbon of emission detected by instrumentation on the IBEX spacecraft in a high-altitude orbit around the Earth, more than 100 AU from the source. One sees it and believes it. I expect that Dave himself will tell us much more about the high points of his remarkable scientific contributions. It gives me great pleasure to turn the microphone over to this year's Parker lecturer, Dave Mccomas.
Margie, thank you so very much for that very generous introduction. So I'd like to start by recognizing my closest mentor, scientific mentor, Jack Gosling, who passed this last year, and who did a humongous service for me and many other people as a scientific mentor. And I wanted to dedicate this talk to Jack and to the others who provide such good mentoring for younger people in our field. Okay, so Jack always taught me to start talks at the beginning. He said, don't assume that everybody in the room knows even the simplest thing about what you're going to talk about. Start at the beginning, at least for the first slide or two, so they have an understanding of where you're going. So I'm going to start with the heliosphere. The heliosphere is shown here in this artist's rendition. The sun at the center of the heliosphere produces a solar wind that blows out all directions in space all the time and basically blows up a bubble in the local interstellar medium. The solar wind is supersonic out to the termination shock, where it becomes subsonic and has to fold back and move away and down towards a tail behind the heliosphere. Out in front, there's a boundary called the heliopause that separates material from solar origin, the solar wind, from material of interstellar origin, the local interstellar medium. And there's either a bow wave or a bow shock, and we can argue a lot about that. It's a very interesting question. So this is the basic structure that we're going to be talking about, our heliosphere. Our heliosphere is very important for a number of reasons, in addition to being scientifically just fascinating. One of the reasons it's important for us to know about is because it's actually the interaction of the heliosphere that does the shielding of the vast majority of the galactic cosmic radiation. And so if you look at the GCRs in at 1 AU, say for an astronaut going from here to Mars, or with NASA's more recent desire to have humans in orbit around lunar orbit outside the Earth's magnetosphere a lot of the time, about 90% of the GCRs at 100 MeV are actually shielded out by this interesting region between the termination shock and the heliopause, something we call the heliosheath, sometimes the inner heliosheath. And so this region provides a very important shield for galactic cosmic rays for the Earth and for the inner solar system. It also acts as the prototype for astrospheres. Similar sorts of phenomena around other stars, where the blowing out stellar winds interact with their local galactic environments. And in some strong cases, strong interactions such as these, they're actually luminous. You can see them in visible light sometimes, this beautiful bow shock here. Or sometimes you can see them in other wavelengths. This is UV, and you can see this long and very turbulent tail behind Mira. This is actually my favorite. And so it's very valuable to be able to study our heliosphere in terms of understanding astrospheres more generally in the galaxy. So I'm going to start with kind of where we were at as a field prior to Voyager arriving at the termination shock. A lot of us had this very simple view in mind. We thought of the heliosphere not so much because we knew it was this way, just it was the simplest way to think about it, as a sphere. The heliosphere was spherical, and the termination shock was spherical. We thought about anomalous cosmic rays, which are basically accelerated at the termination shock, which was thought to be a spherical termination shock. That's interstellar neutrals. They come drifting in from the interstellar medium. They become ionized. Once they're ionized, they're carried out to the termination shock. There they go through shock acceleration for some length of time and produce anomalous cosmic rays. And so we all thought that once Voyager got out to the termination shock, we would observe the unfolding of these anomalous cosmic rays, and we'd see the source of those. Voyager had launched, the two Voyagers, Voyager 1 and Voyager 2, had launched in the 70s. They'd had these tremendous planetary flybys, some of which Fran talked about in the last talk. And then they were on their way, fortunately, out more or less towards the nose of the heliosphere. Voyager 1 is actually very close to the nose, but 30 degrees north. Voyager 2 is about 30 degrees south and also about 30 degrees off on the flank. So these two Voyagers were taking great observations, heading out, and we were all waiting to see what happened at the termination shock, expecting to see the anomalous cosmic rays. But when we got there, we thought we had this huge surprise. In December 2004, here you can see helium, oxygen, hydrogen. You can see that the expectations in these models, the dashed lines, the dotted lines for different models, different conditions, the expectation was that these anomalous cosmic rays at 10 to 100 MeV should have unfolded and should have looked like these models more or less, and they didn't look like that at all. And so this was a really big surprise that the ACR spectrum had not unfolded. At the same time, some of us, in this case Nathan Schwadron and I, had been thinking a lot about the structure of the heliosphere, and as soon as we saw those results, we were right on it, because we'd been drawing the heliosphere and looking at simulations that didn't show a spherical heliosphere, but in fact showed a termination shock that was blunt on the front and extended further out on the back. And this provides a really natural explanation for why Voyager 1, crossing just 30 degrees from the nose, didn't see the unfolding of the anomalous cosmic rays. And that's simply because if you look at the Parker spiral, it's almost transverse all the way around. It takes a year for that to get out near the nose, say 10 months to a year, for the solar wind to get out and touch the termination shock at the nose. But at that point in time, if it's not spherical, on the backside, you don't get to the termination shock, and it takes another 6 months or 9 months or a year in order to get to the termination shock on the backside. And so the particle acceleration can start at the nose, but it really can't continue to accelerate for very much time until you work your way back around and around and around. And acceleration to the highest energies of ACRs takes about a year. So we immediately published this paper and said, look, it's just because it's a blunt termination shock, this can explain it to it, and surely what must happen is as Voyager continues to move out into the heliosheath, we would start to see this unfolding of the ACR spectrum. And in fact, that's exactly what happened. You can see that over the next 6 months of observations, for dates starting in 2014, then going in 2015, this is time going upward basically, you can see the ACR spectrum unfolding progressively more and more. And so the big takeaway from this was that the global structure, understanding the global structure of the heliosphere is absolutely critical for understanding the heliospheric interaction and also the local measurements. So you have to understand your local measurements in the context of this much larger structural aspect. And that brings us to IBEX. The way you get the global structure is by taking images or taking samples from all directions in space, not just some place where you have an in situ measurement or two like you have with Voyager. Those are great, and you have wonderful detailed information at the Voyagers, but you don't get the global information. And so we proposed IBEX back in 2003, launched in October of 2008. It's a very small satellite. It's literally less than 100 kilograms. It's less than a meter in diameter, less than half a meter tall. We used almost all of the mass that was available to us to actually put it on top of another rocket. So they gave us a Pegasus XL, which drops off the bottom of an airplane. And we put our rocket on top of their rocket and took IBEX almost out to the orbit of the moon, where we could get away from the magnetospheric backgrounds, or many of them, and make these very delicate measurements. I'm delighted to say we're currently in our 10th year of extended mission, and we're still taking great observations. So what is it that we're observing? How do we do global observations of the heliospheric interaction from 100, 200 AU away? And the answer is what we look at is charge exchange neutrals called energetic neutral atoms. And these ENAs illuminate the invisible heliosheath. What happens is the supersonic solar wind goes out, crosses the termination shock, is heated, and becomes a hot plasma out here. The interstellar neutrals are floating in from the interstellar medium. Every now and then they pass close to each other. Charge exchange happens, and you create a hot neutral atom that can go flying right back in to the inner heliosphere and be measured by IBEX. It's a very slow rate. We actually see in our peak observations less than half a hertz of signal. But if you design a mission to do that with big enough apertures and all of that, you can actually measure this signal. And so this is the only equation in this talk. So what we're actually observing is the flux of ENAs. It's a line of sight integral along the line of sight of the neutral hydrogen density, the ion flux, and the charge exchange cross section, which is a number like 10 to the minus 15 square centimeters. So this is how you look at the outer heliosphere. I'm going to show you a lot of mole-wide projections. Most of them are going to look like this with the nose in the middle. The South Pole, the North Pole, and the tail is on either side. This is like taking a sphere and flattening it out on a surface like a map. So that's what a mole-wide projection is. While we were building IBEX, Voyager 2 actually crossed the termination shock. That was in 2007. So both Voyager 1 and Voyager 2 were in the heliosheath. They were making measurements. It was the summer of 2009. I was at a big conference, and some theorist, I don't even remember who it was saying, look, we see Voyager 1 and Voyager 2. We see very similar things between them. Surely when the IBEX data are released, we'll see something that's just sort of big, broad structure across the front of the heliosphere. There can't be that much variation when Voyager 1 and Voyager 2 see such similar results in the locations that they're at. Of course, as you already know, that wasn't the case. When we actually got the IBEX observations, what we discovered was that the brightest feature, and completely unexpected and completely unpredicted by any prior theory or model, was this ribbon we call the IBEX ribbon. It happens to pass right directly between the locations of Voyager 1 and Voyager 2, and it's 2 to 3 times more intense than any other part of the sky. So this was a huge surprise. It's really a wonderful example of when you bring new observations to an area, you really push forward a lot of the theory and modeling, and a lot of people starting to think about different ideas of how you can explain such a thing. So we had more than just a single picture because we take ENA measurements at different energies. What I showed you was at about 1 kilovolt. It's interesting that there may be fine structure in the ribbon, but we also have observations that go all the way down to 200 eV, all the way up to 6 kilovolts. And in fact, we have 2 different instruments, an IBEX high instrument and an IBEX low instrument, and you can see at similar energies, this is 900 eV, not quite as good statistics, and at 1.1 kV, you can see basically the same intensity. And so we were absolutely certain that we'd nailed this measurement, and it occurred over a very large range of energies. With all those different spectral measurements, in essence, you can also make observations of the spectral slopes of the neutral atoms. And this, for example, is still from the original science paper, so it's just with 6 months' worth of observations. We went back and we looked at the spectral slopes across the whole sky, and we looked at them in the directions of Voyager 1 and Voyager 2, and you can see we have this good overlap between IBEX low in red and IBEX high in blue, and you can see that we've got the spectra in the directions of Voyager 1 and Voyager 2. We've done a lot more with this over the years. I don't have time to talk about that. The other thing that became apparent right away was that the direction of the magnetic field in the local interstellar medium, which nobody really knew for sure, but there are some things you can do from measurements looking at nearby stars, and it had sort of inferred a direction, and we took that direction. It wasn't that far off of the direction of the IBEX ribbon. If what you're seeing is something where the IBEX ribbon is perpendicular to the line of sight from the sun looking out. Remember, we're at 1 AU, so when we look at 100 AU away, we're effectively looking radially out with IBEX. And so when we look radially out, when the field is perpendicular to that, we basically see that that's the locus for where the IBEX ribbon lies. And these from Nathan's paper, also in the Science of 2009, are 2 degrees apart, these little white lines, and black is at B dot R equals 0. Well, the other thing that this immediately made us understand was that Gene Parker was much smarter than any of us ever would be. Because back in 1961, along with all the other great things that Gene did, he'd already identified the two end states of what this interaction could look like. If you've got dynamic pressure, rho v squared, much larger than magnetic pressure, e squared on 2 mu naught, then you end up with something that looks like this. It looks like a bullet, and you can sort of ignore the magnetic field. If, on the other hand, you have magnetic pressure much greater than dynamic pressure, then effectively what you get is a round heliosphere and drainage plumes, two directions along the local interstellar field. And what we had was the most interesting case of all, and that was an interaction that was sort of halfway between these two. That is one where it probably looks mostly like this, but where the magnetic structure is so strong that it's actually having a strong impact on the shape and interaction of the heliosphere itself. So IBEX exposed that these forces are both important and that we needed to have a much more complicated understanding of the interaction. And so this was the start of a new paradigm, and understanding what this structure might look like. We had the cover of Science in November of 2009 with this image here. If you ask me a question afterwards, I'd be happy to tell you the story of how we got to this image. It's a really interesting story of trying to work with artists in order to visualize scientific information. But this was the start, the kickoff of basically the IBEX understanding. So let me loop back to the ribbon. Very quickly, we had, I think, 13 different suggestions, theories, ideas, models for what could cause the IBEX ribbon. This is just sort of a schematic diagram of things that can cause the ribbon from a review of geophysics paper that we had in 2014. This line here is the bow shock. This line here is the termination shock and heliopause. And you can see here that there are all different sorts of things that go all the way from particles leaking back inside the termination shock, things that happen inside the heliosheath, structures on the boundary like magnetic reconnection or instabilities, things that happen in the local interstellar medium just outside of the heliopause, and even things in the local part of the galaxy, not necessarily related to the heliosphere at all. And so it was a very rich time of people coming up with these really fascinating ideas. But I think the explanation that's had the most traction is one of the ones that we put in the original science paper and followed up on after that. It's a secondary ENA source. It's pretty simple. Basically, you've got the solar wind flowing radially outward. Some fraction of the solar wind gets neutralized because it's so supersonic, it just continues to go radially outward. It can pass all the way beyond the termination shock, the heliopause, gets out into the inner heliosheath where it can charge exchange again, gyrates around the local magnetic field, and if it stays in this narrow distribution where it's got a perpendicular pitch angle, eventually, probably a couple of years, it can ionize again, and then it emits into this pancake shape that's perpendicular to the field. If you can make all that happen, you have something that gives you an emission that's enhanced at B dot R equals 0. And in fact, essentially immediately, Jacob Hirakoisen and coworkers were able to take a model where they did exactly this. They had basically one knob in the model, which was how much of this flat pitch angle distribution, how much to let it widen out. If you isotropize it, you don't get the ribbon, but if you let it go, say 20 degrees, you get something that looks an awful lot like the ribbon. And that's great, except that it's really hard to maintain a pitch angle distribution that looks like that for a couple of years, and the plasma physics desperately wants to break down that distribution. We'll come back to that topic. Okay, I need to pull back for a minute, and Margie introduced this image for me, but I wanted to pull back because it's relevant what the 3D structure of the solar wind is to understanding the IBEX data. And so I just remind you that around solar minimum, you have this fast solar wind that comes out of the polar coronal holes in both the north and the south, and you've got more complicated and variable slow and fast wind down at low to mid latitudes. And so this is a solar minimum structure which we observed on Ulysses and published back in '98. That's important for us because we've basically said we think we might have a secondary source for ENAs in which it's the solar wind itself that comes out, goes through this process and goes back in. I would expect that if that were true, that at low latitudes that solar wind would look like 400 kilometer per second solar wind, and at high latitudes it would look like 700 or 800 kilometer per second solar wind. And we should see that in the ENAs because remember, we're able to tell the difference between different energy ENAs. And sure enough, we're able to do that. This is a little tricky. I've moved from the nose being in the middle of these mole-wide projections to the center of the ribbon being in the mole-wide projection. The nose is actually down here, but this other curve that you see is the ecliptic plane. So what you see here is at 1 kilovolt, 1 kilovolt's 400 kilometers per second for a proton. At 1 kilovolt, you see something that stays within about 20 to 30 degrees of the ecliptic plane, this curve here. Up here, you don't see very much emission at 2.7 keV. That's about 800 kilometers per second, by the way, for a proton. You don't see very much down at low latitudes near this curve, but you do see quite a bit at high latitudes. And at these mid latitudes here, you see a mixture of the two. And so I think this is direct observational evidence that whatever the source of the ribbon is directly reflecting the solar wind and the solar wind latitudinal structure. Secondary ENA source can do that. It's not the only thing that can do that, but it's a really big hint. We were also interested in what the shape of the heliosphere was, going back to Gene Parker's ideas about the spherical heliosphere versus more of a bullet shape. So if you turn around and now you make a mole-wide projection looking back down the tail direction, that is the anti-noseward direction, you do actually see 4 lobes, port and starboard lobes and north and south lobes. This is in the spectral index is how it shows up best. These are consistent with slow solar wind coming out at low to mid latitudes and flowing down a tail that looks like this, with fast solar wind coming out of these high latitude lobes and sort of going down like this. There's even a tilt between the two sides. If you look at this and you smooth it, you get a tilt between the two sides. This is from the inside looking out. This is from the outside looking in, which is why the tilt's in the opposite direction. But the orientation of this tilt is actually consistent with the external field from the interstellar medium, twisting the tail of the heliosphere a little bit from its outside stress, magnetic stress on the outside of the heliosphere. So it all really hangs together quite tightly. Okay, that was IBEX. Let's go back to Voyager. At the same time, I had mentioned that Voyager had crossed into the heliosheath in 2007. Another really important feature of Voyager 2 is that there is a working plasma instrument on board. That instrument failed a number of years ago on Voyager 1. So this is the first time we had plasma observations in the heliosheath, really critical observations. And in fact, the results were quite surprising. There was this fairly large radial speed of about 140 kilometers per second. And there was a flow direction which stayed pretty stable as Voyager 2 kept moving out, and it was inconsistent with flow away from the heliospheric nose. It had far more azimuthal flow than polar flow, and it didn't make sense for flow moving away from the nose of the heliosphere. And if you've got this sort of blunt, bullet-shaped heliosphere, you ought to have flow that flows away from the nose. At the same time, Nathan had been leading a really important study where he was separating the ribbon fluxes from the globally distributed flux. That is the flux that we're getting not from this localized ribbon, but from the entire region between the heliosheath and the heliopause and the termination shock. And by separating these two carefully, he was able to demonstrate that you could integrate and get the pressure of just the globally distributed flux, and it didn't actually maximize at the nose. It maximized about 20 degrees south of the nose. And I remember, I guess I was working on this with Nathan, so I'd seen these, we just submitted the paper. When I saw these other results from Voyager, I remember sitting with Nathan and saying, hey Nathan, I got it. It's not flowing away from the nose, it's flowing away from the maximum of pressure. And in fact, if you take the observed direction of flow, seen at Voyager 2, which is this black arrow, it's not where they expected, which would be the blue arrow, which would be away from the nose. It's way over at this much more transverse angle. And it turns out that that red arrow is exactly the flow you expect away from the bulk of the center of pressure. And so it's doing exactly what you'd expect it to do. You just didn't know where the maximum pressure was. The maximum pressure is not at the nose, the upwind direction. The maximum pressure is about 20 degrees south of the nose. Why is that? That's because of this very strong magnetic field on the outside that's compressing the heliosphere, and because it's inclined from north to south, it's pushing in preferentially on the south side of the heliosphere, and it's making the closest part of the heliopause and the termination shock and the narrowest region of the heliosheath and the largest pressure, all of those things, not located right here at the upwind direction, but located about 20 degrees south. And it's only through having the global imaging and being able to make these global measurements that you're able to understand and put the Voyager flow information into context and understand it. Okay, moving back out to Voyager. Time goes on, and Voyager 1 continues to move out. This is one of my favorite plots from Voyager. This goes all the way back to the 1970s. Voyager was flying by the outer planets. These are galactic cosmic rays greater than 70 MeV. You can see the effect of filtration over the solar cycles going on here. And as it moved further and further out over time, crossing the termination shock here, and we got inside the heliosheath, what we found was a much steeper gradient in the heliosheath and more access to the galactic cosmic rays. We got out very close to the heliopause here, and there's this very steep rise, and then it was very stable. And so this is the heliopause crossing, and once we're past that, we're outside in the local interstellar medium, and we're seeing the galactic cosmic rays outside in the galaxy, basically. But there was a rub, as there often is with these things, and in this case it was that the magnetic field didn't show any indication of a rotation when we got to the heliopause. We saw a boundary in terms of the magnitude of the magnetic field from Voyager 1, but we saw no rotation of the magnetic field whatsoever. And that was shocking, because if these were two different regions with different plasmas that were separated by this boundary, the heliopause, what were the odds that they would have exactly the same field orientation? Seemed very strange. Seems strange to me, too. But when we went back and we looked at and we thought about the location of Voyager 1, it actually turns out that the draping around the heliosphere is reasonably consistent with the same orientation you'd get for the wound-up Parker spiral at 30 degrees, which happens on a conical surface, basically. And very quickly, Ofer and Drake ran simulations where they showed that it wasn't very hard for them to get the draping that was needed in order to exactly match the transverse direction. And so it was possible that they would actually cross the heliopause, and that we'd just been in this very lucky or unlucky spot where it was exactly the same orientation. So I'm going to make my Parker talk prediction today, because nobody's seen the data yet. And so you'll remember it. I actually, no, I didn't intentionally make a typo here, but I'm predicting that the Voyager 2 heliopause crossing that was just announced yesterday, when we see the field data, when we see the field orientation, it's going to have to be a very large magnetic field orientation. And the reason I say that is if you look at Voyager 2 and you see the draping of the external field compared to a wound up Parker spiral there, it's a very large angle. And so that's what we need to see. If that's not true, and we'll see when we get it. If that's not true, then we really don't understand some more things about the heliosphere. Okay, this was all put to rest, whether we crossed or not crossed, and there was a lot of discussion and argument about it by Don Garnett and his team, and that was looking at the plasma oscillations. They showed this 2.6 kilohertz plasma oscillation, which turns out to be 0.08 per cubic centimeter, pretty much what we expected in the interstellar medium just beyond the heliopause. And so this was basically proof positive that we crossed the heliopause and we were in the galactic medium. We saw lots of other wonderful things there. Cremegis, in his science paper, discovered that there were these pitch angle anisotropies when he looked at their lower energy particles. Those have recently been studied over a longer period of time. There continue to be pitch angle anisotropies, both from that instrument and from the higher energy cosmic ray instrument. These pitch angle anisotropies are missing a piece perpendicular to the field, basically. That's been explained or potentially explained by Jacopi and Coda, who suggested you could have a shock that would cross over and you could get a region behind the shock where you basically had compressions of the field at the two ends, and you could have a depletion of perpendicular pitch angles there. My new postdoc, Jamie Rankin, who just showed up at Princeton 2 months ago and was working with Ed Stone before that out at Caltech, has been working with this data for her dissertation. She came out and we sat down and started talking about it. We realized you didn't actually need a shock to compress it at both ends. You've got an already naturally made place for compression because of the ibex ribbon and the pressure up against the outside of the heliosphere. And so if there's anything that closes down the other end, a shock that may or may not have even crossed over the spacecraft, some of the time you don't see these shocks, you have a place where you can get compression between that shock and between right along the heliopause itself. And so it lends itself to a really natural explanation for seeing these pitch angle anisotropies. Okay, so I'd like to come to what is the direction of the local field. So in a series of studies led by Herb Funston, this is just one of them, Herb demonstrated that the ribbon is extremely circular at all these different energies. And if you look on a map of the whole sky, it looks like it's almost in the same place. But if you blow up that little piece of the sky, what you see is that there's a characteristic variation, and that higher energies sort of walk away from where the lower energy ribbon location is. And so we know that it's related to the magnetic field. We know it's roughly B dot R equals 0, but now we see it at different energies. So what is the field direction? That was answered in this excellent paper by Eric Zernstein, who's also working with us at Princeton now. If you have a secondary source, you basically get emissions from different distances outside of the heliopause because of the draping and the unfolding of the draping away from the heliopause. Different energies, which are coming from different distances, which show a different amount of draping. If you take a model of this is an MHD model, if you take a model of the field interaction draping over the heliosphere, and you allow for a secondary source that has this, which we know it does because of the different mean free paths, and you then optimize all of that for a single field direction, you can get one of those, and you actually end up with this very tight measurement of 2.93 microgauss and a very precise field direction. So I think if we're having any kind of secondary source at all, and I'll come back to that topic again, I think we understand the local interstellar field far from the heliosphere at 1,000 AU or 2,000 AU, because we understand how it maps through differential emission at different distances in different amounts of draping. Nathan was able to take that information of the IBEX field direction, put together a very simple model, and basically was able to simulate the TeV, cosmic ray anisotropies, which is a very subtle measurement that's made by Milagro and IceCube and things like that. You can see here the observations, up to 5 TeV on the top and 20 TeV from IceCube on the bottom, and you can see the simulation results. So it all seems to hang together that the magnetic field of the local interstellar medium that we observe from IBEX basically orders the TeV cosmic rays and their access to the near-Earth environs. Okay, let me step back to Ulysses observations. I've already talked about what the solar wind looks like at solar minimum. This is from a later paper in 2013. You can see, again, the same panel that we had, but now you see this as a function of sunspot number. Ulysses actually had nearly 3 full orbits. The first orbit looks a lot like the last orbit, except blue's on the bottom here and blue's on the top here. That means that the in and out direction have flipped, and we know that. The solar dynamo flips with each solar cycle. But what you see here at this intermediate time, when the sunspot number is very high, is what the solar maximum looks like. You see red and blue and fast and slow at all different latitudes, and it's a big mess. And so the simple structure that we see around solar minimum basically breaks down at solar maximum. Well, if you've got enough IBEX data, that's something to look for. And we will. The second thing that we observed in the solar wind was that it wasn't just a solar cycle there was a solar cycle variation in structure, but in addition to that, there's been a general decrease in the output of the solar wind that's a multi-solar cycle effect. And in this paper that we published that was about the weakest solar wind of the space age and the current mini solar maximum, what you see here, I won't show this in detail, but this is the dynamic pressure, rho v squared. And what you see here is that it's been going down for a couple decades. It actually lost about 40% in pressure over this time. You can see that the density and velocity are a function of latitude in Ulysses. You can see how much they vary. At ACE and at other Omni spacecraft, they have a different shape. But if you overplot all that in dynamic pressure, you see that they have basically the same curve, so you can use the proxy of dynamic pressure at any latitude to understand what it is at all latitudes in essence, and it's been decreasing for this whole time. So finally, we had 7 years worth of data. That was enough to really look at time variations, and so we hopped into trying to understand what the time variations of the ENA observations were. This plot shows the solar cycle in red. These are sunspot numbers. In white, this is the dynamic pressure, rho v squared. These are 7 years worth of plots, annual plots from IBEX at 1 kilovolt. You can see here a general weakening of the ENA emissions from time to time, year over year, both in the ribbon and in the globally distributed flux, the other directions in the sky. That's what you'd expect. You'd expect that because if you look back 2 to 4 years, what you see is a solar wind that was diminishing and then sort of stabilizing. In fact, in these last 2 or 3 years, you can see it sort of stabilizing, so there's a really tight connection between those two. So we're feeling like we're understanding how the solar wind is feeding the heliosheath and coming back as ENAs with this sort of 2 to 4 year time lag. Better yet, we now had observations that were several years after solar maximum. And the several years after solar maximum, here with these red labels, 2014 to 15 instead of 2009 to 11, we show again the same plots and the same orientation that I showed you before. And now you don't really see any ordering for the fast wind and the slow wind. What you observe at all 3 of these different energies is pretty similar. Yeah, you get some at that energy at each of these latitudes, but there isn't a clear ordering. And so again, this really looks like a very direct recycling of solar wind, latitude dependent at minimum and latitude independent basically at maximum, back into the IBEX ribbon. So what is the source of the ribbon? A lot of us have come to the conclusion that it's some sort of secondary ENA source. It's lost the latitudinal ordering several years after maximum, reflecting this breakdown from solar wind minimum conditions. It evolves differently over time. That's a more subtle thing. I don't have time to show you that in this talk, but if you look at how the globally distributed flux and the ribbon vary over time, they're not the same. It seems to have a different source, and it seems to come later. There's a bit of a time lag between what we see from a similar direction of the globally distributed flux and the ribbon. That suggests it's further away. And so most of us, many of us, myself included, have sort of adopted a secondary ENA process as the source of the ribbon. Now that said, I told you there was a big problem with the source that Hirakoisen et al. Had, and the one that we were originally thinking about back in the science paper, and that is if you make a narrowly confined pitch angle distribution perpendicular to the field, you tend to generate waves, you tend to generate turbulence, and you tend to break down that orientation and isotropize the particles. So how do you get them to gyrate like that for a couple of years without that happening? Maybe you don't, and maybe it's telling you something else. And so there have been a variety now of other suggestions, one that Nathan Schwadron and I did, which has to do with confinement, actual physical confinement. You actually require the isotropization in order to build up a region where you can increase the density. And so instead of having a narrower pitch angle distribution to get the enhancement, you have a higher emitting source density. In the second one, Phil Eisenberg came up with an idea that basically used turbulence to get a similar kind of result. And then Giacalone and Jacobi had some ideas about trapping in magnetic fluctuations. And so now we're doing detailed plasma physics 100 to 200 AU away with ENA observations. Okay, I didn't point out in that last one, but this is the same plot I showed before. I've just covered most of it up now. And what you can see here was at the very end, there was this there was this large increase in the second half of 2014, which is about a 50% jump in the dynamic pressure rho v squared. Now, we didn't see that in the ENA observations because of this 2 to 4 year time lag. We were seeing solar wind that was earlier, but we basically made a prediction that I've put here having to do with what would happen when this hit the outer heliosphere, produced ENAs, and they came back in, and we predicted that you'd see this enhancement lighting up about 20 degrees south of the nose first in time, because that's the closest point because of this magnetic field pushing on the southern, preferentially on the southern side of the heliosphere, south of the nose. This paper's just been published this year. It's about how the heliosphere has responded to this. We've now moved up to 4.3 keV. This band goes all the way to 6 kilovolts. Actually, it's sort of 3 to 6 kilovolts. We've added 2 more years, or at least another year and a half. This is at the front half of the heliosphere. We've added some more data here. And now you can see in 2017, we're actually seeing the first emission. So after all this time of reduction of the ENA flux, all of a sudden, this large step-like function has gotten to the outer heliosphere and is producing ENAs, which are much more copious, and they're coming in. And sure enough, they're about 20 degrees south of the nose, exactly as we predicted. It's actually more complicated than that. We've done some simulations and tried to put this whole story together. The pressure wave from the second half of 2014 was actually observed out at Voyager 2 in the plasma measurements at the end of 2015. It has to reflect off of the heliopause and back in. You can actually see this wave not just the reflected wave back in, but you can see a wave that's transmitted out into the interstellar medium beyond that. It moves out the termination shock and the heliopause a little, and after basically watching the heliosphere for about a decade contract, it's now finally re-expanding from this major increase, major and long-term increase in the solar wind dynamic pressure. So the timing is really interesting. I guess I won't go into the details of it other than to say there's about 6 months that's needed. It's not just the time it takes for the solar wind to get to the termination shock and cross and get into the heliosheath. It takes about an extra 6 months more than that in order to get the signal back. And that 6 months actually is required because you have to propagate the wave to the heliopause, bounce it back in order to increase the pressure inside the heliosheath. You also have to have a significant fraction of the particles cross the termination shock and start to increase the density in the heliosheath. Those two things, which take about 6 months, once those happen, give you this enhanced ENA emission region, and you start to see about 6 months later, you start to see the ENAs back at 1 AU. So we understand the timing quite well. This figure is from a paper that we submitted 2 weeks ago, hasn't been reviewed yet, but it basically adds another year to the observations. You can see here observations of the dynamic pressure at 1 AU offset 2 years earlier. This is the first enhancement in late 2016 in anti-RAM measurements. This is the early 2017, late 2017, early 2018. There's a difference in intensity between the upper row and the second row because anti-RAM maps and RAM maps are somewhat different. Don't worry about that. Just look at the shape of the relative enhancement. What you see is that we started about 20 degrees south of the nose. We've moved northward quickly, and expanded out to the sides and to the south more slowly than that. That's telling us something very important. We've also done some more simulations. This is a paper that Eric Zernstein led this year, and basically you can see with the predicted propagation fronts where the enhancement continues to propagate out and preferentially goes northward, as you can see here, before expanding out to the sides as much. These are 3 different energies. These are the observations from the just submitted paper at the same 3 energies. And while it's a lot more complicated in the data, I think you see basically the same enhancement and the propagation front moving in the same way. So what that's telling us is this. These ENAs are mapping the closest regions of the heliosphere first. There's normally an enhancement of ENAs observed about 20 degrees south of the nose. Once this arrives, this big pressure enhancement arrives, it really hits that area first. You get the reflection off the inside of the heliopause. You pump up the pressure here. Over the next 6 months or year, that expands out to the next closest regions. Of course, it ran up to the north because this is much closer to the sun than it is as you move to the south or you move off to the flanks. And so we're actually using this step function-like increase in the solar wind dynamic pressure to map out the shape and the closeness of different parts of the front side of the heliosphere. It's a really interesting experiment to be able to run that was given to us by this step function in dynamic pressure. Okay, so I'm close to finishing. I just wanted to talk a little bit about what comes next. After we saw the IBEX ribbon and some of the other early results, we're just blown away by them. A number of us started to say, we got to find a way to have much better resolution and much better sensitivity. I think very visually, I mean, my image was, God, I saw COBE, it was awesome, and then I saw WMAP, wow. And so I was immediately thinking, what if you could fly a follow-on mission that would do for IBEX what WMAP did for COBE? What would this look like? I mean, what would we see in this heliospheric interaction? How much fine structure, how much interaction, how much detailed plasma physics could we do remotely through those sort of observations? And so we started pushing this towards the decadal survey that came out in 2013 as one of the ideas that we thought was worthy of a mission. It ended up being very high in the decadal survey process. NASA put out an AO. We were just selected earlier this year to fly the IMAP mission. It focuses both on the outer heliosphere and particle acceleration inside the heliosphere. We have published already the scientific rationale basically from our proposal. This is an open access paper on Space Science Review, so you can all pull it if you're interested in what we're going to be doing with IMAP. You can also go to imap.princeton.edu, where there's a fair amount of information about the IMAP mission. We're doing this with a very large team, both nationally and internationally. 25 institutions. We're interested in collaborating with other institutions and other people. This is a very large team already engaged in this, but if you're interested in IMAP, let us know, and let's figure out how you can help in some way. So that's pretty much the end of my story. I always like to give you the takeaways, something else I learned from Jack. So my first takeaway is this is an incredible time for the expansion of our understanding of the outer heliosphere and its interaction with the local interstellar medium, with the Voyagers out there crossing these boundaries and making these direct in situ measurements, with IBEX making its remote global observations and putting all that together. The second takeaway is that ENA imaging is absolutely critical to understand the global structure and the detailed physics. I think people who haven't worked with these sorts of observations often think that's not the case, but I hope you've gotten at least a feel from this lecture that it is the case and that we can do a tremendous amount of really detailed work with it. Third, of course, it takes great teams and great teamwork to make these great advances and make things work. And then finally, launching in 2024 is IMAP. And so with that, I'll end, as I almost always do, and say thanks to all of my outstanding colleagues, my friends, my team members, all the people I had the pleasure to work with and continue to have. It's really an honor and privilege to work with so many of you in the community, and I couldn't help for the Parker lecture but to put in a picture of me and Jean from the Parker Solar Probe launch. Thank you very much.
All right, we have time for questions.
Please.
Jeff.
Is there any significance to the fact that the upwind speed is not perpendicular to the magnetic field?
Is there any significance to the fact that the upwind velocity direction is not perpendicular to the field in the interstellar medium? That's the way it happens to be. The direction of the flow is the combination of the proper motion of the sun with respect to the galaxy and the plus vectorially the component of the flow of the interstellar medium. When you add those together, that's the direction of the field. It carries the field past. It turns out that it's inclined about 60 degrees. That's just because that's the way this part of the galaxy kind of wound itself up.
Any other questions? Back there, a little hard to see.
I'll try and yell. Can you hear me okay?
Yes?
So I've heard IBEX described as discovery science. It's brand new. In hindsight, we didn't really know what to expect out there. What do you think are the frontiers left undiscovered?
Well, I'll direct you to our IMAP paper for an extensive discussion of that topic on many fronts. There are lots more things to do. I mean, we've really just begun to use this sort of measurement to divine the really detailed physical processing going on out there. You think they want a beer?
Going once, going twice.
there we go.
There's Zug, Christina.
You mentioned in the beginning of your talk that there was an interesting story or school working with visualization.
Oh,
Can you tell us about
I'd be happy to. Let me see if I can get back to that.
Plant.
Just anyway, it's not a plant, but sometimes if you ask for a question, you get it. So the story of this image that was on the cover of Science was, I'll use this one, was that we had a model, a simulation, an MHD model, and we were trying to get it to render in some way that you could visualize it and you could understand it. And we spent a lot of time and effort on it. We just couldn't do it. I was working with my EPO partner at Adler Planetarium in Chicago. They were great. And they had this graphic artist, and he and I spent a Sunday together, and I'm almost in tears. He's saying, just tell me what you want it to look like. I can draw you anything. And I kept telling him, about field line tension and, all sorts of stuff. And he's like, not getting there. He says, do something that I can imagine. And I said, okay. Imagine you've got like a beach ball or one of those balls that your kid jumps on, bounces up and down, and you're pulling it through a room that's full of bungee cords, which are inclined at an angle. And imagine as you pull it through the bungee cords, how it misshapes the front of that ball and then just put a little tail on it that goes off the side because I don't know what happens back there. And that's what he drew. And that was exactly the visualization that worked to explain what was already in my head.
Okay. Sorry, one more. Sorry.
So my recollection is that there was kind of a poor image of the magnetosphere that you could get from IMAX. Could you get a good image of the magnetosphere with IMAP?
No. No and no. The first no is we had nice images of the magnetosphere with IBEX. They were only suitable for certain things because of the way IBEX observes from the side, basically. But we made the first observations, for example, of the disconnection of the plasma sheet, which we observed with IBEX, and I can give you several nice references. If you flew a mission to really do magnetospheric imaging with the kind of sensitivity that IBEX or IMAP has, you do wonderful work on the magnetosphere. But because we're flying IMAP to L1 and orbiting L1 a long ways from the Earth, we aren't going to take any magnetospheric images.
All right, with that, I think we'll close this session. I want to thank both of our speakers for excellent lectures. Thank you, Mary Lynn. And I'll remind you as you leave that tomorrow is the Early Career Luncheon put on by Liz McDonald. And if you have any questions about the Early Career Luncheon, please get in contact with her or also look it up in the program. And the reception is this evening. Thank you very much.